I want to thank everyone for coming. I want to thank everyone for coming today. Today we're going to be doing introductions to HVAC systems. My name is Christopher Cameron. Today Kelly Krish is with me here answering questions on the side. So if you have any, we'll be going over the introductions a little later as well, though. But I want to thank everyone for joining us today. We're coming at you from the Image Permanence Institute. Coming at you from the Image Permanence Institute here on the Rochester RIT campus. There we go. All right, we weren't advancing for a second. I apologize. The Image Permanence Institute at the Rochester Institute of Technology's campus. The lab has been around for about 35 years. Those of you who aren't familiar with IPI, began our history here in the city of Rochester doing some research for Kodak and film preservation, and over the years have advanced on into environmental research and many other many other research activities. So this is a few of the different labs that are here on the campus at our facility. Today, our presenters are me, Christopher Cameron, Sustainable Preservation Specialist at the Image Permanence Institute, and Kelly is running the questions and answers in the background. So if you have any, please feel free to reach out. Kelly is the Preventive Conservation Specialist here at IPI. Before we go into the presentation, I just want to say, as we go through, if you have any questions, ask them. I'm going to try and answer them as we go, just so that, I always feel bad that we get to the end and have to, go back a dozen slides or so. So feel free to ask them as we go, and I'll try to address those questions while we're on those slides or talking about those topics. So we're going to start off with the first part of this. So the average energy consumption in commercial buildings. What uses the most energy? And according to the Department of Energy, a commercial building is anything that is not residential. So a non-residential facility could be a museum, could be a library, could be a factory. So what are the biggest energy consumers at those commercial facilities? Of course, it's going to be your HVAC and lighting. And today we're going to be talking about that. We're going to be focusing on that HVAC. HVAC is responsible for a significant share of that energy use. Here you can see it's 25 to 30% or more of the total energy consumed in many buildings. And many facilities, many HVAC systems were designed in the 60s and 70s when energy was cheap and energy was efficient. We weren't concerned about conserving it. And, we'll leave the lights on 24 hours a day and we'll make it as, whatever temperature we want and try and hit that as hard as we can because the energy was cheap and abundant and who cared at that time? And we know better now. And, we want to make these things more efficient. So what is an HVAC system? So some simple definitions here. The HVAC system is a system of motors, ducts, fans, controls, and heat exchange unit, which deliver heated or cooled air to various parts of a facility. The purpose of the HVAC system is to add or remove heat and moisture in order to maintain desired environmental conditions. One of the things I'm going to talk about earlier, or I'll discuss a little later, is when we look at an HVAC system, we don't ever add cold, we remove heat. And I'll cover that in a little bit. The HVAC system also provides ventilation and air movement even when not heating or a cooling load is present. Before I go too much into the HVAC systems, I want to really add some safety precautions, and I really want to drive this home. If you're not comfortable around the HVAC systems, please be very careful. There's a lot in there that could hurt you, could cause some serious damage. Be very careful. There's definitely some I guess safety precautions to consider. Always follow your facility's safety procedures, whatever they may be. Have an HVAC staff with you if you're looking at your air handling unit. Carry a flashlight or cell phone just in case. Don't change or touch anything. This is if you do go and look at your air handling units. Make sure that somebody's with you. Do not wear any loose clothing. Things like lanyards, scarves. There's a lot of moving parts. You can easily get hurt or something get pulled into a fan. So please, be very careful when you're looking at any of these air handling units. So one of the first definitions I want to cover before we get into it is what is the difference between a sensible and a latent heat load? And it's important when you look at an air handling unit to understand, or when you consider an air handling unit to understand those. When you talk about sensible heat, it's basically just a change in temperature with no change in the moisture content. If you heat a room up by 4 or 5 degrees, and you don't make any other change to the space, it's just a temperature change. That's the sensible change, a sensible heat change to that room. A latent heat change is the heat that's required to change the phase of a substance. So using an example, that's the condensation at the cooling coil. So when we're actually taking that air, and as we're pulling the air across the cooling coil, the moisture is going to condense into a liquid form. The moisture that's in there is going to condense into liquid form. So we're actually getting a phase change. So that's the latent change, latent work that's being done to the air. So it's two different terms. So when you're talking to any facilities or a mechanical person, and they talk about sensible heat or latent heat, those are the two different terms. Again, sensible is that change in temperature, no change in moisture, and a latent is a change of phase to a substance. So I'm going to go through some standard components of the HVAC system. And our goal here is not to really make anyone an expert, but really to just give you a basic knowledge of how each component works in an HVAC system and what that may mean to your mechanical system. Like if you're seeing any, what the cooling coil may mean, what the filters may mean, what all those play. And if you have someone tell you, we lost our heating coil, what would that mean for your mechanical system in your space? I believe Kelly has popped a question, poll question out to everyone. Yep, she's going to be sending it out right now. And it's just what you feel is the most energy, the component uses the most energy in your mechanical system. And give everyone about a couple seconds to answer. All right. So while everyone's answering, so I'll give a little bit of a spoiler here. It is not our dampers or the humidifiers. About 35% of the energy that is consumed in an air handling unit is consumed by the fans, and 27% is consumed by the cooling coil. That is some data some statistics that have come back from a 2013 government study of HVAC systems on what consume the most energy. So I'll give you a little bit of a breakdown on where those statistics came from. So we'll go start with our air handling unit. So we're going to start with a basic air handling. This is a basic, what they call subcool reheat. And when we look at this unit, we're going to be dehumidifying the air at the cooling coil, and then heating it back up, possibly humidifying and send it back out. So I want to start at turn our pen on and hope for the best, because sometimes our pen gives us some issues, but this is the condition we're hoping for. This is my gallery. Forgive me for not having a great artist representation. It's a clip art, and I get a lot of grief for having used it. But so this is our gallery for our space. And the conditions we're aiming for are 70 degrees, 50% relative humidity, and a 50-degree dew point. So we're going to be pulling this air down through our return. We're going to exhaust a little bit of the air. We're going to return a little bit of that air, and we're going to bring in some outside air. And every step, I'm going to explain what's happening as we go through the filters, the cooling coil, heating coil, as to what each one of those components is doing. So the first thing we're going to do, we're going to take this air. This is the conditions. And in this scenario, everything's working perfectly. Everything's like 100% perfect. Nothing's malfunctioning, or, we hit the set points that we wanted. So we're aiming for 70, 50-degree dew point, and we're going to pull that back. We have a return fan here that's doing this work. It's pulling it through the duct. And we're going to go here. Our first stop are going to be these dampers and this outside air. So first of all, what are our dampers? For those of you who aren't aware, dampers are just the metal doors inside ductwork. They're going to regulate airflow. So the dampers can open or close to, block the airflow, allow air to move. On some older air handling units, your dampers are going to be manually controlled. That means someone actually has to walk up and adjust the dampers manually through an arm that's on the dampers, an adjusting arm. And if on some of the newer units, most of the newer units, the dampers are controlled by motors or actuators that can open or close them in response to, need or demand, or even if you just, choose you want to close off a room for a little bit, you can now control those through dampers. And our outside air, that is exactly what it is. It's untreated outside air that's brought into a collection space to make up for any lost air, exhaust air, or exfiltrated air. So we have that outside air. So one key component in this is the location of the outside air at your facility, and it could play a major factor in this. The image that you're looking at here on the right, that is an outside air intake from a facility that Kelly and I worked with. It's very hard to see. I'll turn my pen back on to really point out, but the outside air intake is here. The reason it's hard to see is there was a tree growing out of it. So it's one of those things, what could happen? What could bring in some possible source of pollution? Aside from this little tree growing out of it, there was also the bus stop for the facility was right outside of this window. It was just outside here. So that could play a major factor. What are we bringing in from that bus stop, what exhaust we be bringing directly in. As a former facility manager, the building that I used to manage, the outside air that was brought into that facility was right outside of the smokers area. So someone at some point in time thought, we're going to bring in the outside air and put the smokers there. And you can imagine the complaints that were happening anytime someone stepped outside for a cigarette. So keep in mind, where could that be located? Some sources of major potential pollution that can be near you: factories, airports, major traffic, fires if they're occurring, storms, or like I said, smokers or even fireworks could cause some issues. Any questions? Okay. So next stop on the air handling system. So we brought that air through. So as I discussed earlier, we pulled that air in from the room. Our air in this ductwork, assuming everything's perfect, we haven't lost or had any change of condition to that air in the ductwork. We brought that air back. We're at 70-50. What we're going to do now is we're going to exhaust a little bit of that air. We're going to return a little bit of there, and we're also going to bring in some outside air, and we're going to have some mixing of that air done here. So we're going to exhaust about 25 to 30% of that outside air. And the reason I say 25 to 30% is we'll lose a little bit in the room. Our goal is to make the room a positive pressurization. When we talk positive, that means our supply is going to have a little bit more air than the return. So this way we're blowing the room up, if you will, like a balloon. So we're going to be pushing that supply air to blow the room up. And on the return, we're going to return a little bit less. So we'll have like maybe 25% air returned. So we're going to be exhausting about 25, 30% of the air. We're going to be returning about 30%, 70% of that air, I'm sorry. And we're going to be bringing in about 30% of that outside air. So we're going to be mixing this return air condition with this. So our next step, we're going to be going through those filters, and filters are exactly what we would believe. They're designed to trap pollutants, dirt, dust, molds, bacteria, and prevent these materials from going downstream, getting trapped on your coils or anything like that. The filters can be made of anything from, we've seen felt, cloth, cellulose, fiberglass, and they depending on the materials, they can filter out varying levels of contaminants. So we can make, this is one of the charts that's available within the methodology guide on our website. It's the standard MERV chart. Basically, what you see in the red box, most museums, most institutes have at least that MERV 8, MERV 7 filter. It's a basic level filter. It's even in many houses. And you could see what those filters block: mold spores, dust, cement dust, snuff, powdered milk. I don't know how much you see either of those in the air, but they're on that chart for potential contaminants that they'll block. You also, with COVID coming on, a number of institutions wanted to move up to MERV 13s, MERV 14s. And giving an example of those are down here. They'll block more materials. It'll also block, cooking oil, most smoke, copy toner. And, as we're down in, say, MERV 14, we also block all the previous things, lead dust, flour, coal dust, things like that. So anything in this, if you're at a MERV 14, everything previously up here, you'll block as well. Yes. I'm sorry, we have a question.
Sure. So during COVID, was any testing done on filters? Was new data learned? What is the best filters?
So a question was, during COVID, was any testing done on filters? Was new data learned? There have been a number of tests, ASHRAE and a number of other institutions recommending moving to the MERV 14s. I'm not sure how much was learned. I know we did our own study. A lot of the problems with the moving up to a MERV 14 filter is one of the things I wanted to cover is if your air handling unit was not designed to handle a MERV 14 filter, if it was only ever designed for, say, a MERV 8, you can't install the MERV 14 because it would impede the airflow. So a number of collecting institutions could install the MERV 13, 14 filters. They wound up having to install alternate methods, things like IR lighting that inside the ductwork, or ionizers that inside the ductwork as well. Some other things. I know some research has been done. I'm not sure exactly what many of the results were, because there's been I personally have seen mixed studies back and forth as to the effectiveness. One study I've seen claims that museums and libraries, because of their filtration levels, are one of the safest places we could be, but I've seen those studies go kind of back and forth all over the map to really point in one direction to say one was better, what's better than the other. we'll bring that back up. I apologize. I appear to have lost my screen. There we go. So back at our air handling unit. So we were able to go through the air handling unit. Now we brought this return air over, and we brought the return air back. We mixed it with some outside air, and now we are looking at the return air, the outside air, and this is our mixed air condition. So we exhausted 30% of that air. We brought in 30% outside air. So that combination of 70% of this return air and 30% of this outside air gave us this condition. So we are now at 73 degrees, 50% relative humidity, and 57-degree dew point at this mixed air condition. So this is assuming that the outside air and the return air mix properly, perfectly within the air handling unit. So we're now sitting at this condition. Problem is we can't send this air downstream to our space. We were hoping we need at least a 50-degree dew point, 70 degrees in the space, and 50% relative humidity. So our dew point's too high, relative humidity is too high, and our temperature's too high. So we have to find a way to bring that down and get that all back under control. So the main component we're going to use to do that, to achieve this, is going to be our cooling coil. The cooling coil also can be known as the evaporator coil, connected to some source of cooled refrigerant, whether it's chilled, whether it's a chiller, a cooling tower. These coils are going to be used to absorb heat. When you talk cooling coil with anyone in facilities or HVAC systems, a cooling coil does not add cold to the air. We never add cold. We remove heat from the air. So it's one of those important terminologies that you want to think about. We're not adding cold, we're removing that heat from the air. So depending on the temperature of that water that's in that coil, this can cause condensation to occur, and that's going to help us reduce that dew point. So as previously shown on the previous slide, we were aiming for a 50-degree dew point, and the air that's going to be coming across is a 57. So if we want to wring that moisture out, get our dew point back down, this coil has to be at least at a 50-degree dew point for us to lower, to remove that moisture and cause condensation, get that moisture we want out of the air. So some quick, we discussed the refrigerants. There's two major types of refrigerants that we use or that we come across. There's DX, which is direct expansion. It's basically refrigerant. It's what you would typically see in a home air conditioning unit, or one of what they call a split system unit. It's typically it's DX, that's your refrigerant. Or there's chilled water, which is at many institutions. It's a mix of chilled water or chilled water glycol. A difference in the types of the cooling. The DX is hydrochlorofluorocarbon gas, mixes with different, there's different types of refrigerant depending on what you're aiming for. You can't say I have refrigerant, so I can only achieve this temperature. Depending on what dew point you're looking for, you can use different refrigerants. There are some refrigerants that can get very, very low temperatures, but they also become more expensive as you get there. Typically, refrigerants require a compressor to move. And the chilled water can get low, obviously as low as 34 degrees. You can mix it with glycol to achieve lower temperatures, and typically requires a pump. So here's our air handling unit. We have now crossed the cooling coil. We are now on the C here side of this unit. So we've taken this return air, mixed it with that outside air. We've crossed, mixed it here. We had the 70-degree, 50% relative humidity, 50-degree dew point. We blew that air across the cooling coil. The cooling coil was 50 degrees. So coming across the coil, we lowered the temperature. And as we're lowering that temperature crossing the cooling coil, we crossed the dew point as well. So we reduced the air, we wrung that moisture out. So here we were getting some condensation. We reduced the temperature to 50 degrees. We reduced the dew point to 50 degrees. Now we have that 50-degree temperature and dew point. Because of that, our relative humidity now is 100%. So here we have a conundrum because we can't send this air downstream. We have 50 degrees, 100% relative humidity. Clearly we're at the right dew point, but our temp and our H are off. So if we send this air downstream, there's potential that we could cause some serious, obviously, temperature issues, but also mold, depending on whether or not we've blocked some vents. So we want to take the first step in there is change our condition of the air. So our next stop on this unit is going to be our heating coil. So our heating coil is a source of heat, can be boilers or electric. And when you talk about heating the air, the coils are actively rejecting the heat that's on them to the air that passes over them. So as the air goes over, the coil is rejecting that heat to that air. and we will have our condition. So we've heated the air only 20 degrees. We've done no other work. All we have done is heat that air. And if you play with either 2-point calculator, or if you're aware of a psychrometric chart, as you change that temperature, as we increase temperature, we're going to reduce that relative humidity. So by adding 20 degrees of temperature, we have brought the relative humidity back down to about 50%. Yes, we have a question?
Yeah, I can speak with temperature. Is return air always run through the cooling coil first?
Question is return air always run through the cooling coil first? No, it depends. There's a number of factors. It depends on basically the design of your mechanical system. I laid out kind of a standard mechanical system in this process, just to give an idea of what each component does. This is what they call a subcool reheat. There are some air handling units where these coils are flipped and it's either heating or cooling only. Really, it depends on the type of air handling unit that you have and the way the system is laid out. I will give some examples of some different units in a few minutes, and it may help kind of give some impression of what other types of units will look like. But not, this is just kind of a standard subcool reheat, not what every unit looks like. And again, my goal was to kind of give that example of what each component does. So when you look at your units, you can say, okay, this is here, so I understand what this component and this component may be doing. But going back to our image here, so we have now left that heating coil. We're at 70 degrees, 50%. So we now have the condition we want for the room, but we have two more stops, if you will, within the unit. We have to cross this E, which is our next component, and then out of F. Well, E is going to be on our unit, the humidifier. It is a mechanism used to add moisture to the air. In HVAC settings, there's really 4 dominant methods. The 2 that we see the most often are these canisters and these tubes with the appear to be the little holes down them. Basically, this will create steam as the air passes over it. The air will pick it up and it'll blend, if you will, and move downstream with the air, change the moisture content. And this is the little boiler. It'll boil the air in this canister, send it through a tube into the unit, and again, reject that air in a similar fashion to this, which will help move it downstream as well. So we've crossed the humidifier. Since our relative humidity condition and dew point are perfect, we don't want to change anything. Our condition stays the same. If this were, a drier season, maybe a winter month, we may want to add moisture. If our dew point was low, or if our dew point was too low, we may want to, top it off, add a little bit of moisture here. But our conditions were good. We don't need any. We need to make any change. Our next stop. The fan is that motor-driven assembly inside the air handling system. For those of you who aren't familiar, haven't looked at inside an air handling unit, one of the reasons I really brought up the being careful is the fan is one of the components that's easy to get hurt around, especially wearing those lanyards or scarves, things like that. So, just keep in mind when you're in the air handling unit, this is one of the more dangerous of the components. Fan motor as well. Fan motor is what drives your fan. In some circumstances, the fan motor can add up to a degree of passing air. Again, I gave the process that everything's operating 100%, where it's a perfect world scenario, nothing is malfunctioning. So, we left our 70 degrees here and we don't pick up any air. So in this scenario, we left our 70 degrees, we returned this air, exhausted some, brought in some outside air as makeup air, mixed it here. We had our condition, cooled air, heated it, and got our, past our humidifier with no work, and supplied that air to the space. So in a perfect scenario, this is how the components would operate together to provide this condition. So there's some additional components I didn't talk about. So some of these components they're not in every air handling unit, but if you're looking inside a unit, if there's a facilities person that wants to walk you around, show you some of these components, give you an idea what's there. It's good to know what they look like. And, so, hey, I know what this is and I know what this can do. Just to get, these are mainly to provide you a better idea of what you're seeing. One is a turning vane. They look similar to dampers, but obviously there's no way to adjust them. They're in a fixed position. They're mainly used to direct the airflow, not make the air as clumsy as it moves through the ductwork. Most of us have been in a space where you've heard the air turn on and you hear the loud banging. Sometimes that could be the clumsy air moving through the ductwork, they call it. In this scenario, the vanes are to help guide the air through the ductwork so it's not as loud or noisy. Another component could be an air mixer. Though this looks like a fan, it's a stationary item. We've also seen some that look like big spaghetti strainers. The intent of this air mixer is to really help the outside air and the return air blend together. So as they go through it, there's a better blend or mix of air on the other side, and there's not, spots or dead spots of like more return air or more outside air. This makes sure that blend is exactly that 73 degrees coming out of this, as we showed on the example. There's also the building management system, is many of you may have, some of you may not. The building management system is going to be that computer-based control system that can allow you to automate the HVAC system. The newer BAMS, which is Building Automated Management System, can control the lighting, security, life safety, multiple systems in one. There's also some other names they give it: BMS, Building Management System; BAS, Building Automated Systems; EMS. So depending on what facility you are, or who you're talking to, they may use different terminologies for that type of system. And I try to include most of the common ones that we've come across or heard below. So also there's our controls or stats. This is the equipment to regulate the HVAC system. Your thermostat, which I'm assuming most, if not all of you have within a space, this is what's going to regulate the temperature. It's going to, do I heat, do I cool? It's controlled by your thermostat. There's also humidistats. Humidistats is the instrument that regulates the relative humidity. This tells your HVAC system, am I dehumidifying? Am I humidifying? Am I adding moisture to the air as it passes? And lastly, there's also that thermidistat. Thermidistat is much rarer. It's not as likely many of you will have it. It's probably a 1 or 2% that may be listening to this that have them, but a thermidistat is going to monitor temperature and humidity at the same time and can activate both within the mechanical system. So while I'm going into that, there's some key vocabulary that you may come across, you may hear in your interactions with different facility staff, and really want to kind of drive those home, give some examples of what those are. One set point.
How about before we get into vocabulary?
Yes.
I think this kind of goes back to the layout of the HVAC. Can you describe diffusers and when they are used?
Yes. So Kelly had a question. Can we describe diffusers and when they are used? Diffusers are typically if you're sitting in an office space or any room you're in right now, if you look up at the ceiling, the vent, Kelly wants me to tip it up at the ceiling. So can you see it? Yep. So that's typically would be the diffuser in the space. Diffuser is typically where the supply air would be delivered to the collection space. And the return grills are typically what the return air gets drawn into. So when we talk diffusers, normally the diffuser would be where the air comes out within the collection space. And again, the grill is where they would be returned within the collection space. Oh, there's another question. I'm sorry.
To vocabulary. How much can the temperature and rate change between the coils and the room itself? And is it common to overcorrect at the air handling unit to make up for heat moisture gained or lost as it moves through the ductwork? Okay, so there's a question of, how much can the air handling unit change? How much can the temperature change in the air handling unit from the room? Is it common for from the air handler to the room? Is it common for the HVAC system to overcorrect? It depends on how your system is designed. We have seen some that are designed compensating for ductwork going through warm spaces. We've seen ductwork that has gone through warm mechanical rooms or even outside and was poorly insulated, or even other warm rooms, and it was delivering cool air to a warm room, and they compensated by instead of sending 60 degrees to the room, they're sending 55 to compensate for the loss that would occur in the ductwork. And we have seen scenarios like that where the system was designed to compensate. Doesn't happen all the time. We have seen where the air leaving the mechanical system, using my example, was 70 degrees. It gets to the room 72, 73 because it picked up heat that wasn't accounted for. And then the mechanical system just works a little harder to compensate. It's not always the case, but sometimes some systems will compensate or are designed to compensate for that loss of the air coming out.
So going back to the vocabulary here, the set point is a temperature at which the thermostat has been set. That's when we all talk, I need 70 degrees. That's the set point we're aiming for. The response time is the time required for the control to reach a new set point following a change. An overshoot, the amount the control goes beyond the set point following a change in load or a change in set point. And that deadband is the temperature range that utilizes no heating or cooling. So wanted to find a way to really almost display these. And I think this is the best example I could find to show exactly what is meant when someone discusses overshoot or deadband or response or set point. So here we have the set point for the unit is this dotted line that's running here. We'll say this is 70 degrees. We're aiming for 70. There's our 70. So the response time, we make a change in set point. So the response is, we adjusted the set point. So we were at 68. So here's the response. Okay, the unit is now conditioning to 70. We go, but we pass it by. A lot of times, many air handling units, especially some older units were designed where they overshoot. So if we're aiming for 70 degrees, we may go to 72. And it's typical for the air handling unit to do that. So it overshoots just slightly. And it overshoots to say at 72 degrees. And that's where the thermostat will say, okay, we're at the right condition, and it'll stop the unit. And once that air handling unit stops, we'll have some drift, and we'll be in this drift, which they call the deadband. And the temperature will slowly drop. We'll go from 72, 71 to 70. We cross that set point, but we still doesn't come on yet. Then we maybe hit 68, 69, maybe 68. And at that point, the unit will say, okay, it's time to turn back on. And then the unit will it'll turn the unit back on to go back to that the set point, or try and reach the set point again. So when they discuss deadband overshoot, this is one of the things that they're keep in mind. And the period is the time between when we hit temperature and then sat idle in the deadband until we reached till turned on to reach the set point again.
So would the number of visitors affect the efficiency of the system?
Yes. Would the number of visitors affect the efficiency of their system and how it would respond? The number of visitors can affect a lot. We actually worked with a museum here in our city that had huge visitor attendance. I mean, hundreds of people every day, and they were aiming for about 72 degrees in a gallery. And one of the things that they were doing is they tried bumping the temperature back down to 68 degrees in the wintertime because, hey, we can bump that temperature back down, use a little less energy. And what they found was, even though they bumped the temperature back down to 68, the number of people in their galleries in space were still keeping that temperature at 70, 71, 72 degrees, just the amount of people within that space, the body heat from individuals. And even there was a slight moisture uptick from the attendance as well. Not major, but attendance, occupancy in a space includes both heat and some moisture as well. Sorry. And if you're looking at this graph and wonder why it tapers off in such a manner, this was a graph that's designed to show newer, really high-tech efficiency thermostats. And the newer thermostats are designed to learn over time and kind of compensate for the overshoot in the deadband and learn to almost phase them out, if you will, and be more efficient with energy use.
If you reduce the deadband, if you can, does that reduce the overshoot? Is there a way to minimize the overshoot? If
you reduce the deadband, can you reduce the overshoot? Depends on your system. Some older systems we've seen can't change that. But if you reduce the deadband, reduce the overshoot, you can reduce the deadband as well. And does it what was the other half of that?
So it was if you reduce the deadband, does that reduce the overshoot? Is there a way to minimize the overshoot?
Yeah, and is there a way to minimize the overshoot? There is. I mean, again, the newer thermostats that this graph is from really is what that's about. It's showing that a lot of the newer programmable thermostats, the smart thermostats, are learning to compensate and reduce those deadbands and overshoots. And some of the programmable HVAC, some of the systems, some of the really good HVAC techs can play with the BMS and find ways to toy with this as well. In my facilities work, I worked with a phenomenal HVAC tech who was able to manipulate the HVAC system to kind of correct for some of the overshoots and deadbands really well. Yeah, and then, but the tighter, Kelly does bring up a good point. I apologize. The tighter the deadband, the less energy efficient we are. So we've seen some institutions recommending 2-degree deadbands. It's really tight. I believe the DOE, Department of Energy, was recommending at least a 4-degree deadband at least. So just keep in mind, the tighter that deadband, the more energy, the tighter that band, the more energy you're going to use to hold it. Next component is a variable frequency drive or a variable speed drive, otherwise VFD, VSD. You may hear facilities staff call them, they have called them freak drives or speed drives. Basically, this can be within your institute to control the fans. Adjusting the speed on this can reduce the supply air or the return air for the fans. And these tie into what is called an affinity law, which is a cubic relation of horsepower to CFM. And basically what that means is if you lower the horsepower 50% on a fan, that doesn't mean you have 50% air moving. If there's a cubic relation. So if you want to reduce the airspeed to, I believe it's 80%, you actually can lower the fan to about 13%. So a significant lower, and you'll get about 80%, still have 80% of your CFM moving. And there's a copy of the affinity law within our methodology guidebook that's available on the IPI sustainability site as a download. Gives an example of what you're looking at when you think about that affinity law. Desiccant air system, desiccant wheel or desiccant dryer. It's a hygroscopic material that rotates with inside a mechanical system. As this wheel rotates, some of the air is going to come in contact with the air from your facility. Some air is going to come in contact with regeneration air. I'll give an example of how this operates in a little bit, but wanted to include it because it is a component that you may see in an air handling unit. And those of you, mainly want to include this picture who have a desiccant and wondered what the wheel looks like. This is a very large version, about 4 feet, but this is a large version of what that wheel will look like, and that's inside your unit that's actually removing that moisture. One of the last items I want to talk about within your air handling units is open plenum design. The image on your right is the exact opposite of the open plenum design. Open plenum is when your air is returned from your HVAC system right into the ceiling, an open ceiling of the space without the use of ductwork. So we really don't recommend it for collection spaces. We want to keep that air as contained as possible. So the air, comes to your room in a ductwork, is distributed to your collection space. And then when it leaves the collection space, we want to see it leave within ductwork as well. All too often when we see issues within collection space, that's because the air goes up into the ceiling and it'll mix with air from wherever. I mean, it could be from wherever, it can collect dust or wherever. And as it moves back to the unit, the condition can significantly change because of that open plenum design. And lastly, here we have the economizing. The economizer is a part of the building's cooling system that uses cool outdoor air of the building instead of operating the air conditioning components. As an example, we were aiming in that example I gave earlier, we were aiming for 70 degrees, 50% relative humidity, and just happenstance, say outside, those conditions were very close or a little cooler than what we wanted. Then they would bring in more outside air, or maybe even 100% of that outside air as a source of cooling rather than running the cooling coils on the system as a form of free cooling for the unit. So Kelly's going to post up another question for everybody, types of HVAC systems that you may have. And just out of curiosity for anyone, if they if you know what HVAC system you may have within your facility. And give everyone a few seconds to answer.
First of all, people answering that. There's 2 questions here.
Okay.
So first of all, would tighter deadbands result in more wear on the system as well?
Question is, would tighter deadbands result in more wear on the system? It's going to be more energy. I can't say it's more wear on the system. It's going to definitely lead to more energy use. You're going to use more heating, more cooling to achieve those conditions. But I can't say for sure that would lead to more wear in the unit. I mean, again, you're going to require more heating or cooling.
Yeah, another question was, we tend to focus on temperature and relative humidity, but are there any recommendations for mitigating noisy HVAC systems and supply vents/diffusers? Oh,
there's a question. We tend to focus on temperature, relative humidity. Is there suggestions for noisy ductwork HVAC systems? if it's the system itself for noise, there's not much we really can do about it. Unfortunately, we've seen some pretty noisy ones. But for the ductwork itself, there is insulation that can be wrapped around ductwork. Please don't put it in the ductwork. Kelly and I have seen too often some of the older insulation rots over time, and as that insulation will rot, it breaks down and winds up coming downstream onto your collections. So you're past your filter, you're past any point where anything can filter that. And as that breaks down again, it's going to come downstream, end up in your collection. So you can insulate the ductwork, and if possible, they can install some of those turning vanes. We have seen that done as well as a method to try and reduce the noisiness within the ductwork. Okay. All right. So I'm going to go over some different HVAC systems now.
So 67%.
All right. So I'm going to cover some different HVAC systems. And again, this is really giving you some examples of what you're used to, and then what you may have seen, what you may know of. And now that I've explained some of those components, what they mean and how they work together here. So this DX system, this is basically your Windows style air conditioning unit. And typically there'd be a wall separating the two of these. But this is what would sit in your window. You're trying to cool your apartment, your office. You have your condensate coil. This is where we're going to reject that heat back out into the air. And this is our evaporator coil, where we're going to remove that heat. When they talk about heat pump, we're literally pumping the heat via this compressor, which is the C. We're going to pick up the heat here and pump it over here, where we're going to remove it to the outside air. So when you look at this unit, when you're the room side of the unit, which is here, you're going to be looking at the air is just moving like this. We're not bringing in any outside air. There'll be some vents in the side. It'll bring the air in. The fan will blow it across the coil and remove the heat, and it's just exhausted into the room. So the air is basically making this little bit of a circle. On the outside, same thing. We're bringing some air in. It's blowing it across the coil, which is picking up that heat and pulling the heat off. And if you're wondering, these arrows are the motion of the refrigerant within that unit. So we're going from a liquid, we're picking up that heat. It's now a hot liquid, and then hot vapor, and then gets pressurized, becomes a pressurized vapor through the compressor, and then becomes a liquid again as it's picked up that heat. So it gives you a rough idea of what this type of system looks like. And here are some examples. Those window style units you see. Even the split systems that a lot of institutions have, we've seen these, a lot of historic buildings have actually started installing some version of these. What is inside your space is the room side of that unit, and then your refrigerant literally pumps the heat all the way outside to the condenser, and then that condenser is going to reject that heat and then pump the new refrigerant back to the unit. And some of these package units also operate the same way, depending on the style of package unit you have. So here is back to the example that I discussed originally, is the, we crashed. Yep, no, we didn't. So back to the unit we discussed originally, the single zone air handling system. This was that basic unit I designed, I explained earlier, where we're going to return that air, we're going to exhaust some of it, we're going to filter some of it, and then we'll pass it through the heating, the cooling coil, or cooling and heating coil, I'm sorry, and exhaust it into space. The question that was asked earlier, the design of this, there can be a number of different designs just to this unit alone. So what I gave here is a basic example. In one scenario, these coils can be flipped where it only heats or only cools. And in that scenario, we will not do any dew point change. The air will just be, as we discussed earlier, sensibly heated, sensibly cooled. There can be what they call preheating or pre-cooling coils, where there's a cooling coil that's going to precondition the air before it gets to the coil. So depending on the type of system you have, it could be different. Just this style alone could be different.
Maybe in relation to this, do you also want to comment on how the size of a room in relation to the HVAC system can affect reaction time, like reduce or increase fluctuations in overshoots?
Yeah. The size of the question about the size of the room increasing reaction time for the HVAC system and overshoots. The larger the room, the larger the air handling unit, you may, depending on the way the thermostats are set up, get different response times from the unit. We have seen larger systems with multiple thermostats being averaged, if you will. So if you imagine a large rectangular room and there's 4 or 5 thermostats that all are recording and taking an average temperature, And that temperature is what the unit's responding to. That large room may be conditioned and some of the thermostats may not be satisfied yet. One may be satisfied. So you may wind up with, a dead zone here, a microclimate, if you will, until all the thermostats or most of the thermostats need, are calling for conditioning, and then the unit may either turn off or back on, depending. So larger unit could cause some more fluctuations or issues with that, especially depending on the size, the layout of the unit, the type of the location of the sensors, the number of sensors. There's a number of factors that play into that. So going to take you through like almost a time machine, but we've seen many institutions having these, so I want to make sure I cover all of these. The first unit is a multi-zone air handling unit, and it is exactly what it's described. So imagine the unit I described earlier, that subcool reheat. Instead of one room, here we now have multiple rooms. And again, I apologize for my clip art. I take a lot of grief for having used these, but we have a gallery space, we have a collection storage space, and we have also this little cafe here with the little chef. And the issue with this type of space is these were installed in the 60s or late 60s to early 70s. They're very inefficient systems because what the big conundrum is with these units is I'm creating a condition for human occupancy, for collection storage, and then for this food space, which is again human occupancy, but I have other issues like food and things like that to compensate for. So I'm going to return, I'm say trying to achieve 70 degrees here, maybe 60 degrees here, and maybe 72 here. So I have to return all this air back to the unit and then cool it down to the coldest condition. So now I have to cool it down to 60 degrees to satisfy this room. And then as I send it back out, then as the air goes out, and I'm going to heat it to, again, 70, 60. I'm not going to heat it because I'm at 60, and then I heat it to 72 to bring it back and do it again. So I'm doing multiple conditions. I'm using a lot of energy to achieve that. Another unit, a very inefficient and expensive unit to operate, are the dual duct air handling units. And these are still, they were installed to the late 60s to the early 80s. And these are still very prominent. We see these a lot in institutions. Basically, again, this unit is exactly what it is as well. It's a dual duct. So as I showed you that unit earlier that had subcool reheat, now imagine that we have, our air is going to return from this unit and come back. And then we're going to pass it over some filters. Our filtering is done here. And again, this is our outside air. It could be located here. We've seen it located here. We've seen it located here. But we're going to bring that outside air. We'll bring some outside air in. We'll mix. And now the air, once it leaves the unit, splits in two. And the air is going to either be cooled in one duct, 50% of it can go one way, or 50% of it can go the other. It could be 30-70, depending on the design system. Most of the time it's 50-50. So your air literally splits in two. So now you're going to send 50% of the air cooled, 50% cooled air, 50% heated air. And we'll use, this room as an example. I'm trying to make, a condition here. I'm going to have to, they're going to regulate the doors on these dampers, the doors on this box. So it's going to mix the amount of each air, cooled and heated air, to achieve 72 for here and 60 degrees for here to satisfy that. Again, then I have to return that air back and do this process over again. So mixing conditions as well as very inefficient. I can't, dehumidifying with these units is very hard to do because you're only dehumidifying 50% of the air. You're getting one swipe at 50% of the air as it goes. So those of you in historic houses are going to ask, I have forced air. What does that mean? Well, this is that type of unit. This is that forced air system. So look at that. And as I described that, those split systems, the air conditioning unit, would be a similar scenario here. So we would have the evaporator coil inside, and then the refrigerant would be pumped outside to the condenser. So we would do our conditioning here. This may be one of the ways it cools. If those of you who are in a warm climate like Florida, maybe Arizona or Texas may have what they call the heat pumps again. And basically this system would be able to reverse the flow of the refrigerant, if you will. So you'll be able to, this can go from cooling and heating, and if you ever need it, can be, heating and cooling, depending on what you may need. But for the most part, this would be a cooling system. You may have also a heating coil on here as well. So the air would be exhausted out of here, up through a vent in the floor, into the building, and then there'd be a return grill on the floor, and it would basically draw back in air through the building and then start the process over again. And you would have different types of exhaust vents and fresh air vents. So this would be a burn off vent that would go up and out of the roof maybe, and this would be a vent that would pull in fresh air from outside. So induction heating units, we still see a fair amount of these in collection spaces as well. Some are still in use, some not as much. If you want a really good example of what an induction unit is, all of us have stayed in a hotel, and typically that is what is on the wall in the hotel. It's basically just a simple unit, maybe not always having pre-treated air. This is just, some do and some don't, but I want to include it. So they may be some form of pre-treated air, but the air in the room will be exhausted, come back out in this circle, be brought in through the vents somewhere, most likely on the bottom. The fan will pull the air through, push it out, and you'll either heat or cool. This will likely not do both. It will either cool the air sensibly or heat the air sensibly, and then reject the air back out into the room. So again, we're back in that, this is that sensible condition I was talking about. We're not doing any moisture removal. Any moisture removal of this type of units just happenstance. So we're just going to do that sensible condition change and then just keep this moving in this circle, if you will. I discussed the desiccant air system earlier. We're starting to see more and more of them installed in institutions. And I wanted to cover exactly what that looks like. So if you have any questions, exactly what the design of that air, how it moves. So if you're looking at the desiccant, here's that giant wheel that I showed earlier, and the air is going to move through that unit. The air is going to be brought in through the unit. It's going to come in typically through the bottom vent where the bottom arrows are, across right to left. And that is the air from the space, the processed air. You're going to be bringing that air in. You're going to be taking that air. It's going to cross over the coil, cross over the wheel, if you will. And then the fan's going to exhaust that air into space after it's crossed the wheel and been dried out. The balance of that air, so if this would be typically like 60 to 75% of the air is going to cross this bottom part. The top part of the wheel is going to cross the what they call the regeneration side of the air, and that's going to cross over a heating coil, which is going to essentially superheat that air. I believe, I've seen some information that says it's about 212-ish degrees for one unit. So it's going to superheat that air, blow that air across the wheel, and it's going to pick up a lot of the moisture that was on the process side and then blow that air out of the building. So the top U vent duct that you see here, that's going up and out of the building entirely. So this air it'll come through your building, but doesn't get exhausted anywhere in your building. This is pulled from outside and exhausted outside. And the bottom duct is, within your collection space or air handling unit and outside of and back to your collection space. All right. So the next unit system we're going to talk about is the variable air volume unit, and it's also called the VAV. And I apologize, my computer is hung up for a second. But the variable air volume unit is the newer, more modern, energy efficient method. Do you have a question? Oh, sorry, we do have a question too.
Just before you move too far past the desiccant wheel, can you answer, can that be added to an old system? Their system is from the 60s and they're told there's no option for HR.
So there was a question, can a desiccant wheel be added to an older system? And the question is, depends on your system, depends on the system you have. Whether some older systems may not be able to have a desiccant added to it. Some can. It really depends on the type of system. You'd want to work with a mechanical engineer to ask them that. We've seen there are desiccant systems that can be added as a secondary system. So I believe Munters is one company that comes to mind, but they make a mini desiccant system that can be put within a room to act the same as one that we would be put within a wheel. So you can maybe not add it to the system, but maybe add it to the room to help as a secondary form of dehumidification. So here's the variable air volume system that we were talking about. And this would be you would have that standard subcool reheat system. This may be a secondary component. The temperature is controlled by the volume of air that's discharged into space via the dampers. If you can see where the C is, that's going to be controlling right here, the air that's going into the box. If it doesn't want air, if the room doesn't need an air change, they can close those dampers. If they want to move air, they can. The red coils there, sometimes heating coils, not present in all units, but they can be present in some. So I put them in there as an example. But you can top off a room if you need just a little more heat to a space. There can be added, and these can be combined with those speed drives or frequency drives to really make them efficient. And these are being used more and more often as one of the more energy efficient ways to produce an environment within a collection space. One of the last types of units is just a dedicated outside air unit. It is never really a typical or standard type of unit, but the purpose of this unit is to pre-treat any outside air before going to the other unit. So some of the conditions we discussed earlier, the heating or loads in the hot, moist air in the summer, the cool, dry air in the winter, puts a load on an air handling unit, and the units have to compensate for that. Some institutions have dedicated outside air units, and that unit is going to treat the bulk of the outside air that's coming in before it sends that air onto the other units themselves to use. So that load, that moisture load, if it's a hot, damp summer, that unit will remove that moisture, remove that heat, and then pass along usable air to the unit, to the other units, so it's less work that they have to do. And again, these are also more energy efficient methods being recommended.
Chris, can you recommend, are there any other ways to reduce energy consumption in tropical climates?
Any other ways to reduce energy consumption in tropical climates? One of this type of unit, the dedicated outside area would be a good way, but it would be, I mean, I would have to look at, it's almost like, I hate saying it, a case by case scenario, because it depends on the facility, the conditions they're trying to achieve. But we were actually worked with a couple institutions in Louisiana and I believe Florida that had a dedicated outside air unit, and that was their main method for breaking that high heat, high moisture content that was coming in, to really get that condition and then send it to the other units. But I'd be happy to talk more about that, because unfortunately, it depends on the where and what you have currently to use to be able to change that condition.
Sorry, just going back one.
Okay.
Is VAV the same as a VRV?
Is VAV the same as a VRV?
Yes.
I'm not sure I've heard VRV.
Okay.
Sorry.
That's it.
I've not heard VRV, so I can't answer that.
Okay.
Doesn't mean it's not the same, because as I said, I've heard variable speed drives. I've heard about 8 names for variable speed drives. So VRV could be the same. I could be. Going to go over a couple other things here. Some typical pitfalls we see with HVAC systems. I think Kelly has another poll question she's going to send out. So it's just some questions we have of issues you may know of or have seen or experienced within your collection space or within your own institutions.
Okay, Chris. So I think just to add to that, variable refrigerant volume.
Oh, yes. Okay. Variable refrigerant. Sorry, that I have heard of. Yes, variable refrigerant is it's not the same as a VAV, but can operate in a similar manner. I actually have a slide for this in another presentation, but it's not in here. It's, if you imagine a room that HVAC system serving multiple rooms, that split system where the refrigerant is being sent to the individual rooms, the VRV can control the amount of refrigerant that is going to different rooms. And it's another very energy efficient method that's being recommended, because they can control conditions and refrigerant flows. And if a room is satisfied and doesn't need the condition, they can literally turn the refrigerant off, if you will, and not send any of that. So it reduces the energy consumption by that space if it's satisfied, if that makes sense.
And then I think you may have addressed this just towards the end, but does a dedicated outside air unit reduce energy costs?
Does a dedicated outside air unit reduce energy costs? The answer is yes and no. Having that unit, you're going to have more cost for operating that individual unit. There's going to be the more cost for, obviously, you have another unit that's going to be using energy to heat, to cool. But in the same respect, you are no longer doing the extra work to dehumidify, to humidify at the units, which reduces some of the strain or stress on those units, if you will. If you imagine that subcool reheat, what we're thinking of is every time we're bringing that outside air in, we're having to dehumidify that. And if we're only dehumidifying at one unit, then we're only doing the major amount of work at one unit. That leaves the other units to really just do some sensible cooling as opposed to that dehumidification. So you pay more to run the main unit, but you're doing a lot less work cumulatively to the others by not having to dehumidify at those units. So no, you use more, but a lot less.
Okay, so you're at 74% participated in the poll, and it looks like high humidity is by far our biggest issue.
For those of you who didn't hear, we got the results are back, and for those of you, I don't know if everyone can see them, but high humidity came back as the main concern or main issue that a lot of experience, along with high temperatures, low humidity, and broken components as well. So some of the typical pitfalls we see for HVAC systems, and this would be the worst, are blocked supply and return vents. So boxes stacked up too high, dampers on vents closed, restricting airflow. If you're thinking about your collection space, if you're looking at your space, try to give the air at least 18 inches of clearance so that it can move or at least mingle with what's in the room. And using a worst case scenario, worst case example, is I'll cite this scenario here. This isn't exactly where it took place, but using this as what could happen. We had that subcool reheat system where we're reducing the temperature to 50 degrees. We're at 100% relative humidity. We have very cold, very damp air. We then rely on the heating coil to heat that air up so we can send it out to the space. In a couple scenarios, we've seen that heating coil has failed. And when that heating coil failed, we now have really cold, really damp air that's coming down this ductwork into the boxes that don't allow that air to mingle in the space. We've had instances where mold has just covered this box, materials within the box and below. So you want to make sure we're giving that air some chance to move and mingle, because in the event of a failure, excuse me, you can have some really significant issues if you don't catch that failure in time. Some dirty missing filters as well. Filters should be changed and cleaned routinely. Fouled and dirty filters, replace them as you find them. I know this goes a lot to the facility staff, but it's something for collections to keep in mind. HVAC system should never operate without its filters. And if you operate it, you're going to clog up your coils very quickly. And as I discussed earlier, upsizing a filter, if you're using a MERV 8 and ASHRAE is recommending a MERV 14 for COVID safety reasons, you can't, most units, it's not just plug and play. You can't just pull an MERV 8 out and put a 14 in. When you upsize those filters, as you go up on the MERV scale, the more you impede the airflow. And if your system was not designed to adjust for that or to compensate for that, you can put some strain on your systems, which could damage some components. Yes.
Are PureFill systems still being used for chemical pollution filtering?
Are PureFill filters still being used for chemical?
Maybe you want to just answer about chemical pollution filtering beyond like the filtration that you talked about with MERV.
Oh, it's for like the gas.
Activated charcoal.
Okay, sorry. Kelly was correcting me. Are some of the other filters beyond the regular standard MERV filters are some gas phase filters. A lot of institutions use them to remove some of the gaseous pollutants that are in the air. A lot of film storage will use them to remove some of the acetate smells and such that are in the air. So yes, we still see a lot of gas phase filters used in collection spaces in many institutions. But again, your system needs to be designed or to be able to compensate for that. Otherwise, just installing those filters could wreak some havoc in your system.
And how often should they be checked and cleaned?
How often should your filters be checked and cleaned? Again, that's a little, I'm sorry for loaded answers, but again, that depends on a number of factors. It depends on where your institution is, how much outside air you're bringing in. We've seen institutions where they're located next to a major highway, major source of pollutants, and they're changing filters every 2 or 3 months. And then we have actually worked with some institutions that are out in, middle America, out in the suburban surroundings with not much around it, and they're changing filters maybe once every 6 months to a year in some circumstances. So it all depends on what's around your building, what could be causing some pollutants. and even maybe what types of filters you have. Your HVAC staff have what they call magnet helix, and I know I have one in the cabinet, but the magnet helix on some air handling units helps show the airflow within the it helps show the static air pressure within the unit. And whenever that goes off, whenever the gauge starts to show the airflow change, then they can go and say, hey, the static pressure in the duct has changed, so we need to reduce or change the airflow or change the filter, I mean. So it's one way that they'll use to go by static pressure as well. Oh, I didn't even talk about this. I apologize. Broken dampers. Broken dampers can restrict airflow through an HVAC system. They can stop air from entering a room. We see this a lot, especially outside air dampers and what they call fire dampers. So fire dampers divide a firewall from one room to the next. They're inside a ductwork. They divide that ductwork in the firewall, and they're designed to close in the event of a fire. And in some circumstances, it's not even poor maintenance, but they just fail over time. And we'll work with an institute that says, hey, it's stuffy, there's poor air movement, I have a microclimate. And many times it turns out that the fire dampers have failed, or even the outside air dampers have closed and have rusted shut and they're just not opening. So broken dampers can be a major fault and a major cause for either poor airflow or lack of outside air, things like that. Unbalanced system. Balancing your system is important. When I was working on my certified energy management class, one of the things that they discussed is even a lead building. If you have a lead building 4 or 5 years down the road, even maybe even 2 years down the road, as staff change, as staff make adjustments within the building, can set the building out of balance, and that can cause some energy issues. So making sure a system is balanced, and there's no real set, like I should balance it every 4 years, 5 years. If you move rooms a lot, if you're adjusting spaces and adjusting collection spaces a lot, you definitely consider balancing a room. If you're changing use, or if you're looking at galleries and you're moving gallery walls and things, you might want to consider balancing that system, because over time, as we're changing uses or as we're changing functions, even as we change employees, different employees will put different settings or components, and that changes the use of the balance of that system. It can throw things out of whack. So it's good if you have questions about the airflow in a space, if they're getting dead, if you're in a large room and 2 or 3 diffusers have airflow and a couple diffusers don't, and it's good to question that balance, maybe question the air balancing in there, maybe have a balancing checked by this by a specialist. Sorry. And lastly, in this, we're going to talk about some sensors not being calibrated. This can be a huge fault. On an HVAC system, your sensors should be calibrated roughly every 5 to 7 years. Most sensors, even your data loggers, can go about 2 to 3 years without needing to be recalibrated. So for some of the lower end ones can maybe 2 or 3 years, but decent loggers, decent sensors can give you about 3 to 5 to 7 years without needing to be recalibrated. And you really want to think about that. So if we've worked with institutions that have never calibrated their sensors, 20, 30 years of existence, they're still using the same sensors. And we've seen in a circumstance a sensor that was 15 to 20 degrees out of calibration. And if you ever want to check it, it doesn't hurt to get a brand new data logger, get a recently calibrated data logger, and put it next to the sensor. What does the logger read? What does the sensor read? What does your brand new calibrated logger think is happening? What does the sensor for the room think is happening? And just a way to checks and balances for your own space, for your own system. So lastly, we have a question.
Are we gonna?
Yep, we have one last poll for you all.
And while it's in mind, can you describe what's involved with balancing?
So in balancing, and I will actually see if I can go back while we do that. So in balancing, when we talk about balancing, you'll see that there's that little red hood, and depending on the whoever's your balancing specialist, may use different systems. They'll put that red hood literally right over a diffuser. They'll check the CFM of the air coming out of that. They'll compare it to, if they have them, the original prints of the unit, to what the unit was designed for, the original prints for the space, and say, this room was designed, or this diffuser was designed to put out 400 CFM, and it's now putting out 220. So they'll know that they have to make maybe an adjustment in there or in different diffusers to kind of, it's almost like managing water flow. If you want a certain amount of water flowing out of this spigot and you're running it out of several others at the same time, then you got to adjust all the different spigots so that you getting the right amount. It's similar with the airflow. They're going to have to adjust different diffusers around a room to get the balancing right. And typically that little red hood that is shown in this image is what they'll use.
You would also related to this section, is it recommended to have a regular scheduled cleaning of the ducts themselves, not just the filters?
Is it recommended to have a regular scheduled cleaning of the ducts? If possible, yes. It's great for me to say. I mean, I'd love to tell you, yeah, get them cleaned as often as possible. Realistically, it's an expensive endeavor. I'd love to tell an institution to get them cleaned. You should get them cleaned. As crazy as it is, I've seen ductworks where the duct itself was full of mold. So, and that was granted after a hurricane scenario, but it doesn't hurt to have your ducts inspected and cleaned, but it can be a costly scenario. And I mean, that's not something to do every few years. That's something that would probably have to go out, 5, maybe 10 years, depending on the institution, depending on the funding that's available for something like that.
Okay, so 50%.
Okay. See that Kelly was giving us numbers that we see the numbers of who does. Can everyone see the poll? Okay, that 58% don't have a management system. Then it's important to look and work with your facility to create that management team. Having that management team will help establish a good process forward on what to start doing to make changes for your collection environment. And I've mentioned it a number of times, but the IPI sustainability, there's a resource. We have the methodology guide. It's got some processes on establishing that team. We're happy to help out. And if you have any questions, feel free to reach out to myself or Kelly. Going over what you can do. So some simple basic, how do we make this right? What do we do going forward? Monitoring your spaces is huge. Collecting your temp and relative humidity data are important. Granted, we want to know where the collection lives. What is it experiencing? But beyond that, we very highly recommend those regular walkthroughs. Regular walkthroughs are going to be very important. The advent of the wireless systems are great, but we can't assume that what we're seeing in the data is 100% correct. I have seen a very large library collection space that had very good data logging. I mean, a big collection space, they had 7 or 8 data loggers throughout the collection space. And they wound up having a huge mold outbreak that occurred in between data loggers. And the problem really was they were trusting the data loggers and they didn't know, I kept the compact shelf closed here and I didn't need to go in there as often. I just pulled what I needed, got to the data, and they were trusting the data too much and not really doing a good walkthrough. So you really don't sacrifice that walkthrough because we're getting data and assuming the data is going to save us. You want to communicate with and collaborate with your facility staff, report any concerns as soon as they arise. Can't stress, the communication part's huge, but also when you work with facility staff, try and make it as concise as possible. As a former facilities person, some of these staff individuals, especially on university campuses, can be handling 3, 5, even we worked with one individual who's handling 13 buildings. So try not to over inundate. We had an individual who told me they were having trouble communicating with their facility staff. The person wasn't responding. And I said, well, let me see the email you sent. And it was 5 pages long. And it's too much. The facilities, they need to know what's going on so they can just, take action and get it fixed rather than take all the time to read it. It's just in some instances, they don't have that time. Again, don't block those vents. If you can, give it that 18 inches. And when it comes to understand your risks, one of the major things in there, establish a reasonable set point. We've been on projects, we've been called in, the collection staff, we've worked with facility, we've asked facilities, we want 65 degrees and 45% relative humidity in this space. We have to have that. And then when we talk to facilities, the first word out of facilities mouth is, yeah, we can't do that. We can't achieve that. The mechanical system was never designed to achieve that. So work with your facilities to come up with some reasonable set points. What can we realistically do? Manage your outside air a little bit better. Some energy efficiency measures are, if you can't really shut off the outside air, which we never would recommend, just kind of reducing that consumption. But if you're concerned about that consumption reduction, especially for galleries or so, can you reduce it to on-demand ventilation or demand controlled, where you're having a CO2 sensor that is tied to the actuator for the damper. So if conditions get to a certain point, the CO2 sensor will open the dampers and let more outside air into the space. Also, some things, side note for contaminated outside air. Contaminated outside air could be anything from, fires going outside or dust. So some ways to mitigate that. In the event it's short term, the last month I've actually had this question come up twice. What do I do in the event of fireworks at my outside of my museum? The fireworks are going on directly overhead. What do I do? If it's a scenario like that, it's after hours. Look into turning the system off for that time, just that short period of time that the fireworks are going off. Try not to bring in whatever pollutants may be brought upon from the fireworks. If it's a short fire, like God forbid there's a fire in a structure nearby, can we shut this system off for a little bit to not bring in whatever contaminants can be dumped in the air? If it's long-term, a major fire, something like that, is it possible to close the outside air dampers? We have worked with some institutions that have worked with their local government agencies to come up with a plan to close the dampers when the major fires happen, because that's all they can do. Or maybe can they install some of the gas phase filters, as we talked about earlier, for removing that smoke, or even a MERV 13 filter if your systems are capable of handling those. For those of you in the collection, make sure you support that continual maintenance. Ensure that all the belts are tight. Make sure they're in good shape. The filters are being changed regularly. Make sure all the heat transfer. I know it's easy to say, but you don't want to ride the facility staff, but at least, it doesn't hurt to ask, hey, if we changed our filters, recently, excuse me. It doesn't hurt to ask about the system being balanced. If you know the humidification's not in working order, help work with the facility staff to get it fixed properly. And if one of the worst things that hurts is turning off faults or alarms. They're there for a reason. And if a fault or alarm goes off, try not to ignore it, or try to figure out what's causing it, and either rectify the alarm or fix the problem. So don't just turn them off and walk away. And also some benefits of commissioning. We want to make sure that everything's working. So when they talk commissioning, it's having an agent of some kind walk through your facility, assess everything and say, yes, the system's functioning as it's intended. And it's good to have that signature, like brand new building, it's designed to do what it did for X, Y, or Z reasons. You're good to go. Identify some defects before you're out of warranty. You don't want to see, something fail and realize the warranty expired and you never got it checked beforehand. It helps reduce some energy consumptions and reduces your, environmental impact as such. It helps facilitate, it helps your facility have thorough documentation. So having that commissioning done, you can have a thorough documentation that your building was inspected by X, Y, or Z, and this is what they found, and helps you, going forward, have that process of, is anything wrong? Is everything right? And lastly, for something like having a preservation commissioning done, helps you achieve the best and preservation environment for your mechanical system. Helps you make sure, you're using the right amount of energy to achieve the right condition within your collection spaces. So just wrapping up a few things. If you have any questions, if you have any concerns, feel free to reach out to me or to Kelly or myself. Their IPI offers a range of services, sustainable resiliency, data analysis. If you're using Climate Notebook and you just have questions, let us know. Film storage assessment, mechanical system design consultations. We're happy to help out. Talk to us. Feel free to reach out. There's also some grants that are coming up. All this information is available on the IPI Inch Permanence Institute website. There's a work with us page where it has all the links to all these grants on there. The NEH Sustaining Cultural Heritage Grant is coming up. It closes, I believe, in January. If you have projects within your institute, would highly recommend considering either a planning or an implementation grant for that. There's also PAG grants and CAP grants, the IMLS Museums of America and IMLS Inspire grants. The last on there, there's the database for state incentives of renewable energy. It really is called Desire. I wish I was making that up, but I'm not. It's a government-run website where they list incentives that are locally available to your institution. So if you're in, say, New York, what may be available in New York, and you can look up your area, and it'll tell you what energy or renewable energy incentives may be available for you. And it may be like installing solar panels. There may be, grants available for that, or incentives available for that. And one last thing to wrap up, we are planning a series of 2-day workshops, sustainability workshops. I believe our upcoming workshop will be socially distanced, and we are planning one for Washington, D.C. in November. So if you're interested, there will be a brief survey at the end of this presentation. feel free to reach out to Kelly, myself, say so in the survey, let us know. Again, it will be socially distanced following all, COVID safety protocols. And we are also hosting a webinar on December 3rd, and I'll be covering some of the best tools to use if you want to do an evaluation of your collection space, if you want to do, evaluation of what's happening in your facility, what are the best tools you should be using. So I'm gonna open up to any questions, and there's the website, the IPIsustainability.org, where the methodology resource is available, as well as the Image Permanence Institute, where you can go to that work with us, but it has links to all those grants and the Desire site, so you can go look at that information as well, and our contact information. So do we have any questions?
No.
Okay.
Okay. How do you speak with the facility staff about the need to balance? Do you ask for a balancing unit? Is that a specialty that they should have?
All right. How to speak with the facility staff about balancing? Is it something they should have? Depends on the size of your institution. Some facility staff may have balancing equipment, some may not. That's almost a, does your facility have the equipment? Do they have the skills? Are the staff trained? I've worked with institutions. We've actually done projects with institutions where it's a university. There's a number of staff on hand, and there were trained staff members on hand that could actually do balancing, or even employees on site that just did balancing. And we've also worked with some museums where it's a small museum, they don't have that staff. It doesn't ever hurt to ask. One of the tools that we'll discuss in the next workshop is an anemometer. It's a little handheld fan-looking unit. We have one in the cupboard there. I can show you that. But if you can use the anemometer. Anemometer will help you. That's not a great end all be all, but looks roughly like this. And if those of you who could see the image, and I'll stop sharing so you can see me. So the anemometer will look like this, and the anemometer will give you a good idea of, are you getting good airflow? And we've used it to identify no airflow is moving whatsoever out of a vent. And taking that information, that was the collection staff were able to give to the facilities and say, okay, can we get some balancing done? Can we get this fixed?
I don't know.
Oh.
Do you know why magnesium sulfate crystals would grow on the surface of interior HVAC ductwork?
That I don't know. A question is magnesium sulfate. What is the word exactly? It's an anemometer. Can you type it in the chat? Yep, Kelly will send the spelling in the chat, but it's an anemometer. There was a question about a magnesium sulfate crystals growing in ductwork and would I know why? And fortunately, I do not know why that would occur. That's a head scratcher, but I would be more than happy to look into it and help you try and figure out why that's occurring. But we've seen a number of things growing, but I've never seen that.
Okay. Let's ask this question then. Are systems different in the European Union versus North America, or basically the same? I asked in some countries might have different.
Yep. A question of our air handling systems different in the European Union than the United States. Design, yes, there can be some drastically different designs, how the system is laid out, how the system may be, the airflow may go through the system, but the components should generally, your cooling coil, and it's one of the reasons I wanted to walk through those individually, is your components should be doing obviously the same process. The filters, the cooling coil, depending on the dew point you're looking for in the space, that's where it's going to be achieved, potentially going to be achieved, and your heating coil doing that. So yeah, the design is likely different from the European Union to the United States. Even South American units, we've worked with a couple institutions, Brazil, that have different units, but the overall components do the same function, if you will.
Okay, one more question about balancing.
Yeah, okay.
Can you balance when you don't have the original specifications of the AHU?
Can you balance when you don't have the original specifications? I've seen, we know it, I know it's been done. We've worked with a couple institutions that have done it. We worked with an institute that they lost all the blueprints, all the information was gone. And they actually worked with a mechanical engineering company that helped them create a balancing plan, if you will, for their site. So if you have questions about that, I would talk to a balancing agent, HVAC. A mechanical engineer should be able to work with you on that, help you come up with a plan, and may tell you is it's feasible or not feasible. But I can see that they should be able to help come through with a plan on that.
Okay. What would you say is some of the most common avoidable mistakes made in retrofitting, renovating, upgrading HVAC systems for cultural heritage.
Okay, what are some of the biggest mistakes made for updating HVAC systems for cultural heritage? Number one, not moving thermostats. We have seen you'll move walls, but you don't move the thermostats. It's like the movie Poltergeist. You never move, you only move the headstones, you don't move the grades. It causes more havoc than ever. When you imagine an air handling unit was designed to serve a specific space, a specific area, or a number of areas. And as we start changing rooms, changing airflow, changing the design, we've seen rooms walled off and they've walled up, blocked the vents and moved the thermostats in a room with no vent. And that just causes havoc. It's being thoughtful or mindful as to when you're laying spaces out, when you're going to move walls, when you're going to move spaces around, how is that air going to flow and how is that going to affect the thermostats? Not moving diffusers is another. Changing use of rooms. I discussed a multi-zone air handling unit where it handles, 2 or 3 different air handling spaces at once, where it's collections, and you'll have a room that's designed to only do system that's designed only do human occupancy spaces, and then they'll take one of those spaces and change it into collection storage, and now the unit can't do that design. Similarly, we've seen collection or spaces that were designed for human comfort. I've seen roller skating rinks and car dealerships transformed into collection spaces, and they never change the mechanical systems, and the mechanical system can't give you a preservation quality environment because it was never designed to achieve that. So typically, without being really mindful when you're making those changes, you can cause some problems that may not stand out or jump out immediately, but just give you headaches continuously until you try to resolve them.
Okay, so there's 2 different questions regarding condition.
Okay.
So one is, we have a room that gets condensation forming on the ceiling during the summer. The floor above is a large walk-in. Their space is 68 to 70. Any thoughts on why that might be?
Okay. Question was condensation forming on the ceiling of a space where the room was conditioned was to 68 to 70 degrees. The space above was a walk-in cooler. It is likely when you're looking at condensation, it is the dew point of your space needs to be below the temperature of the surface that you're considering. Sorry, I'm trying to make sure I said that properly. What? Kelly says we have a handout on this that we can make available to everyone after this. So the surface, if you have a walk-in above, the surface of that floor is probably below the dew point of your collection space. So as the air in that collection space is, the floor could be 55 degrees and you may have, 56 degree dew point. It could be that simple. And if you're at that dew point and the surface is below that dew point, the moisture is going to begin to condense on that. It can begin to condense on that surface. And I'm happy to work with you more and talk with you more about that to discuss that issue.
Another question was, their HVAC maintains lower temperatures and RH in the winter and higher in the summer. Would it be better to have the same conditions year round?
So it maintains lower RH in the.
It's lower temperature and RH in the winter.
Okay.
And higher in the summer.
Okay.
But would it be better to have it the same year
No,
round?
the condition basically should we have a year-round temperature or relative humidity condition? We would recommend, if you can't, if you don't need to not, and basically using separate set points for the summer and set points for the winter, it helps reduce the energy consumption for your facility. Try to use some passive measures. If you are aiming for, say, maybe if you have to achieve, say, 72 in the summer because of temperature, exterior temperature, but when you get around to cooler winter conditions, can you back that temperature down a bit? And is it referred? It's not. We don't typically refer to it as seasonal drift, but I guess it can be.
Seasonal drift to get to seasonal.
Yeah, you can, as Kelly said, you can use seasonal drift to get to it. We call them seasonal set points. And when we had that IPI methodology, can you send the IPI sustainability?
Yeah.
Okay. So the link to the methodology has almost a step-by-step for looking at implementing some of those seasonal set points and those seasonal strategies. Even doing day and night set points, if you can, to do the same thing in the evenings. If you can set it back in the evening to do some passive measures, take advantage of those cooler evenings, how can we go about that?
Okay. I'm gonna go ahead and we'll continue with the sustainability part. So how do dead bands and the need to minimize short or sharp changes in conditions relate? Are dead bands to some level desirable or necessary?
Are dead bands desirable? Unfortunately, they are a bit of a necessary evil. Let me see if I can bring that slide back up, because the deadband, when we're looking at it, are going to be it's going to be with the way that our HVAC system is needs to function, for lack of a better term. Some of the older thermostats are going to be aiming for that dead band. Got it. Okay, so let me share my screen now. So some of the older HVAC systems aim for this overshoot. They're going to have that overshoot built into them, and the deadband is going to be almost a natural function in there. So it almost becomes, for older systems, I can't say a necessary evil, but an evil that exists, an inherent evil. For some of the newer systems, it can be, they can operate better, especially with, as I said, the newer smart thermostats, to try and undo that, to try and phase them out, if you will. Does that answer that?
Yeah.
Okay.
Are you likely to have problems switching the air handling unit on and off as needed, or are they designed to run continuously?
Okay. Is the air handling unit designed to turn on or off, or is it designed to run continuously? That comes down to your unit as well. We have worked with older air handling units that are on an older air handling unit, and I'm talking mid 80s. Now I'm not talking very old. Older air handling unit, mid 80s, that was on a BMS system that could not be shut off whatsoever. If you shut it off, it erased all the computer programming and it had to be redone from scratch. But we have also worked with units from the 60s that were on, modified to BMS, that could be turned off and on routinely. It's definitely something to work with your facilities on. That's the process we have is in the methodology as well, but it's definitely something to look into. There could be significant energy savings. We've worked with institutions in hot, humid climates, in libraries that were built in the 20s that could shut their system off for 4 to 6 hours in the summer, in the evening. And that's, even in the summer, in a bad building that they were shutting it down for, got significant energy savings. So I definitely would recommend investigating, looking at shutting that system down. Has been concern in the past that shutting it down, turning it off will cause a lot of wear and tear on motors. I've been told that that's been debunked, that theory isn't entirely true, that you don't put as much wear and tear on motors as was believed. So that there's the concern over burning the motors out isn't as strong as it used to be, or as it once was.
So we're at 3:30, so.
Okay.
You wanna-
If there's more,
you wanna answer that?
if there's more, I'm happy to answer a couple more questions. If everyone's done it, doesn't want to hear me anymore, I understand that too.
Okay, so will changing from a gas-powered boiler and electric chiller units to a heat pump system have effects for other parts of the system, such as the air handling unit?
Well, changing from a gas-powered boiler and what was it?
Changing from a gas-powered boiler and electric chiller unit.
A gas-powered boiler and electric chiller to heat pumps have negative effects on the air handling unit. It's hard to say. I want to say no, because if they're properly designed by, if a mechanical engineer is taken into account, if it's something that they've accounted for, all the loads and everything in the system, it should be, if it's done properly and planned properly, it shouldn't. But that I don't want to speak broadly and tell you, yeah, it's not a problem. But we have seen instances ourselves where certain components were replaced and it wasn't thoroughly thought through, and it has had a ripple effect kind of down throughout the facilities, other air handling units or other adjoining spaces, or spaces just touching that, happenstance that have a problem. So
Okay. There's another question about the HVAC system blowing in the spaces and disturbing the collection.
Okay.
Can fan air be reduced?
Yeah. Question: can fan air be reduced? The answer is yes. Well, like everything, yes, you can reduce your fan if your fan was designed to be reduced, and if the fan has a fan, you have to have a VFD on it, of course, which were the fan, as we discussed earlier. You have to have a VFD on it to be able to reduce it. If you have a VFD and the fan can obviously be reduced, and you can save significant energy. You can, the concern about, the artifacts blowing, you can back the fan speed down. Again, you have to talk to your facility, because you may serve other rooms. If that air handling unit's serving 3 or 4 other rooms, backing the fan speed down is going to affect other spaces as well. But if it only serves your collection space and you're okay with reducing the fan speed, you can definitely reduce, go in there and back the fan speed off. And again, using that affinity law, you can, reducing the horsepower doesn't even significantly reduce the CFM. It's a cubic thing, and you can see that there's that graph affinity law in the guide that really breaks that down and shows you how that relates.
How do you improve the efficiency of your HVAC with the construction materials of your building?
How do you improve
the efficiency of your HVAC given the construction materials? Of your
Okay,
building?
how do you improve the efficiency of your HVAC given the construction materials of your building? That's a tough one. It's one of the things we can recommend is it's tough to say without knowing the type of facility. You can judge how your mechanical system would respond if you have. I say this to a few individuals who want to test outages. They want to test system shutdowns with their, get better energy efficiency by shutting down. Do you have any data from a power outage? Do you have any data from a storm came through, knocked power out for a day? Do you have that data? Did you collect that? And we'll look at that together and we'll take that data and can we build, okay, you lost power in, it was a leaky building. You have a structure that was built, in the 1910s. And you had a power outage, but hey, the building did better than you thought. You held condition for 4 hours with the power out. Okay, well, that's great. We know you can do at least 4 hours. And you started to maybe start to lose condition. Can we look at a 3-hour shutdown? It's 3 hours, we're saving energy, but we know we can hold 3. So maybe if we can do a 3-hour shutdown, can we span it out and do that 3 hours 2 or 3 times during the day? So if we do it 3 hours and then run for 6 and then 3 hours and then run, we can potentially save 9 hours worth of energy in the day if we're staggering that properly, if we know the limits of our facility. So there are ways to work around it. It's just, getting to know your facility and some ins and outs and limitations at the end of the day. We're good. All right. Thank everyone for listening. If you have any questions, again, feel free, reach out to Kelly or myself. I'll display, if this will let me, our information. And, we're happy to answer any questions. Even if you just see strange information in your data, you need help trying to figure out what in the world that means. Happy to talk that out and try and figure out what's going on with you. But until that time, thank everyone for listening, and we will see you all in a month, hopefully in December.